Rainfall is not like that. If you measure rainfall in a flat area during during the occurrence of a frontal system, which means a large perturbation, large meteorological perturbation, that's fine. You can measure the rainfall in Bologna, and it applies also 20 kilometers far from Bologna. For river flow, you can't say that. It's just valid for the given measurement station. So rainfall is more easily available, and therefore people have the idea, starting from about the first ideas were developed in about 1600, at about 1400 years ago, around 1600, people realized that maybe that from rainfall data we can reconstruct river flows. This is called rainfall runoff modeling, or in Italian it's called a flussi dei flussi, modelli a flussi dei flussi. And they started to develop this idea. And as I said, the first guy that probably had this idea was an Italian priest living in the Umbria region in central Italy. He had the idea of measuring rainfall and trying to reconstruct the river flows. Keep in mind that when you say to people, especially in international context, who was the first one to develop an idea, you get into trouble, because usually we know that in Italy people started observing hydrological processes first, let's say, earlier than in other countries, and this is why we have the longest rainfall series in the world. But my experience says that when I go to an international conference and they say the first guy who had the idea of developing a rainfall runoff model was an Italian priest, then I get at least 10 people saying, no, the first one was my country, and etc. So when one talks about history, it's always, but I am pretty sure that the first idea was developed in Italy to try to reconstruct the river flows starting from rainfall, but the actual reality is that so far we didn't succeed in a satisfactory way. But still, in water resources management, rainfall runoff modeling is widely applied, widely. So this is why I consider this as a pillar, this subject as a pillar of this course, and I want to dedicate some lectures to it. And let me just say, we are running out of time, but I wanted to show you the first slides of the lectures that you can download. By the way, I updated these slides today, small change, very minor changes, but now it's better if you download again, very minor ones again. And basically the principle of rainfall runoff modeling, we start from, let's skip the introductory slides and let's skip this one which I already showed to you. But basically what is the purpose? The purpose is to write a mathematical model, a set of mathematical relationships to reproduce these mechanisms. So basically our question is, I know rainfall and I want to reconstruct the surface outflow for a given domain, again, for a given domain, which we will define later. And basically, I have to emulate these processes, and to emulate them, I build a mathematical model, and a mathematical model is nothing else than a set of equations. Which are fed by input data, rainfall, and deliver some output, which is river flow. Let me anticipate one subsequent watershed. This is what we want to do. Sorry. This is the actual process. We have rainfall over a considered domain. I will define next time what the watershed is. For now, just take that it's your domain, and then the natural system produces the runoff. In mathematical terms, we have what we call a rainfall runoff model, which is a set of mathematical equations which receive in input the rainfall, plus maybe other variables we will see, because sometimes temperature and the snow are extremely important, and then delivers an estimate of the runoff. Of course, this system, this mathematical model is affected by uncertainty. I say, of course, because you already know that when we talk about hydrology and water resources management, uncertainty is always there. So this is our purpose. And again, I go back to the beginning. The purpose is to reproduce this system. And this is a sketch of the natural system. This is a sketch of the mathematical system. This is a lot complicated. But basically, this, if you look at these boxes, we have the same names than the processes in the previous slide. Let's look at these boxes. There are surface runoff, overland flow, which means flow over the length. And then there is somewhere groundwater flow, infiltration, subsurface flow. Subsurface and groundwater, it's a subtle difference. Subsurface is what is also called hypodermic flows, means in the upper part of the ground. Groundwater usually indicates the flows that takes place in the deep underground. And then you have transpiration, interception. I'm not sure we already defined it, but no problem, we define it. Interception is the water that is taken by the vegetation, by the leaves and the trees. And so basically this is our mathematical box, which mathematical model, which aims to emulate the natural processes. And then let me just recall to you that in hydrology and fluid dynamics, conservation of mass and energy, as well as Newton laws apply. So basically the equations that make up our mathematical model, the candidates for these equations are conservation equations of mass and energy and Newton laws. These are and this is why hydrological models are called physically based models. Okay, you will see that in practice, the models are not as complicated as you may be concerned of by looking at these premises. And our aim in the next lecture will be to look at the details. I will lecture on Thursday and Friday. Friday again with the PC. We move forward with R and the first applications. And again, I will make available the slides used by Emanuele on Friday, last Friday, and the videos. I go in the office now and I put them there. Let me see if, yeah, everything